Based on Ohm's law, phasor relationships, and the Pythagorean theorem, you have derived formulas which enable you to calculate the total voltage, impedance, and current in an RC circuit. Now that series RC circuits have been thoroughly examined, let's see how a parallel RC circuit differs.
According to Kirchhoff's voltage law, you know that the voltage in a parallel circuit is the same across each branch. This holds true for a parallel RC circuit. The resistive, capacitive, and source voltages are all equal, both in magnitude and phase.
The same two types of relationships that were introduced in connection with series circuits will serve as guides for parallel circuits as well. They are phase relationships and Ohm's frequency relationships.
Let's investigate the phase relationships on graph paper as was done earlier. As you saw with series RC circuits, the resistive voltage is in phase with the current through the resistor, and the capacitive current leads the voltage by 90 degrees. Remember, these phase relationships will always be true for each of these devices respectively. The difference with parallel RC circuits lies in the fact that the voltages are in phase. This time, the capacitive current leads the resistive current by 90 degrees. Here is the phasor diagram. I sub C leads I sub R.
Just as you've seen that phasor diagrams and the Pythagorean theorem can be used to determine total voltage in series RC circuits, they can also be used to find the total current in parallel RC circuits. Let's try an example.
In this parallel RC circuit, I sub R equals 3 milliamps and I sub C equals 4 milliamps. Use this form of the Pythagorean theorem. I sub T equals the square root of the quantity I sub R squared plus I sub C squared. This yields 5 milliamps of total current within this parallel RC circuit.
The other basic type of relationship also holds true within parallel RC circuits as well as within series RC circuits. Ohm's frequency relationships. Once again, there is no relationship between resistance and frequency, and there is an inverse relationship between capacitive reactance and frequency.
The calculation of total impedance in a parallel RC circuit is done in a similar fashion to that of a series RC circuit.
To determine the impedance of a parallel RC circuit, you can use the Ohm's law relationship just as you did for a series RC circuit. Z equals V sub T divided by I sub T. Let's go back to the example with a 40-volt source and a total current of 5 milliamps. The circuit impedance then equals 40 volts divided by 5 milliamps, which becomes 40 divided by 5 times 10 to the minus third. This yields 8 times 10 to the third, or a circuit impedance of 8 kiloohms. Stop the program and complete activity number 3. When finished, continue watching the program.
You now have the tools as a technician to solve for the total voltage, current, and impedance in series and parallel RC circuits. If you have any questions, be sure to view this section one more time. All of the RC circuits examined so far have been analyzed at one frequency. Now, based upon what you already know, let's analyze how each device in an RC circuit will respond to variable frequencies. To do this, you'll need to investigate the relationship between voltage and frequency. This can be done by applying concepts you have already learned.
To start, you know from the second basic relationship that capacitive reactance is inversely related to frequency. You also were presented with a version of Ohm's law that can be used to find capacitive reactance. Rearrange this formula to solve for capacitive voltage. V sub C equals I times X sub C. Now exchange X sub C in the formula for its equivalent value, 1 divided by 2 pi Fc. Doing the multiplication yields V sub C equals I over 2 pi Fc. This new formula, which was derived from what you already know, reveals the relationship between capacitive voltage and frequency. They are inversely related.
Let's examine this relationship on a dual-trace oscilloscope with the input frequency on the upper trace and the capacitor output on the lower trace. Here, the inverse relationship between voltage and frequency in an RC circuit is demonstrated. When the frequency is high, the voltage across the capacitor is low. At low frequencies, there is a large AC voltage across the capacitor. This RC series configuration is commonly used to allow only a range of low frequencies to pass and not higher frequencies. Because of this, when you take the AC voltage from across the capacitor in a series RC circuit, you have what is called a low-pass filter.
Now let's determine what the frequency response will be if you take the AC voltage reading from across the resistor instead of the capacitor. Again, this response can be determined based on what you already know.
Again, you must find a way to relate the voltage and frequency mathematically. This can be done by looking for a quantity that takes frequency and resistance into account. Let's work with impedance. Start with Ohm's law for resistive voltage. V sub R equals I times R. Remember, according to Ohm's law, that current equals voltage divided by impedance. Substitute this equivalent value into the formula for resistive voltage to get V sub R equals V times R divided by Z. Now replace Z with its equivalent value, the square root of R squared plus X sub C squared. Because you want to understand the relationship between frequency and the resistive voltage, replace X sub C with its equivalent value, 1 divided by 2 pi Fc. Now examine the formula. An inverse of an inverse yields a direct relationship. Therefore, as the frequency is increased, the resistive voltage will increase. On the other hand, when the frequencies are low, the resistive voltage will be low. Because of this, when you take the AC voltage from across the resistor in a series RC circuit, you have what is called a high-pass filter, where only the higher frequencies are passed.
You now have a full set of tools for the successful analysis of RC circuits. Let's stop here and review what you've been shown.
In this video, you've seen how the total voltage in a series RC circuit and total current in a parallel RC circuit can be calculated.
Two important types of relationships were presented: phase relationships and Ohm's frequency relationships. These will serve as useful guides when analyzing RC circuits.
Impedance was defined and calculated.
Finally, you saw the effects of a variable frequency on the voltage and current in a series RC circuit.
The concepts that have been presented are used in the AC analysis of many practical electrical and electronic circuits. Look at this video one more time if you have any questions. In the next video, resistive inductive circuits will be thoroughly examined.